Yes, John. The barrier potential across PN junction. Yeah. Good morning, Priyam and Tithi. I think all of you got little bit of idea what I am talking about. The depletion region thing I discussed last day only. I hope you all remember. Let me decrease the altitude.
Yeah.
Do you have any doubt regarding the depletion region?
So,
Okay, fine. So today I will be redrawing it. Actually, I told last day also that our main interest is around the junction, the neighborhood of the junction. Sorry. This should be a perfect rectangle. Okay, I was looking at the screen, so it got. Anyways, there is no hard and fast rule that you have to draw P here and N this side, but almost all the books that I have come across so far over the years, they draw it like this. Okay, you can draw N here, P here also, but the explanation should be correct. I'm going by the convention the most of the books follow. Okay, so this is this side we have what we call, what are these ions called? The minus things,
accepted.
right? Acceptor. They have the tendency to accept. These are the donor ions, right? And this is in fact still the junction. I hope you all looked into the video that I sent last day in the group. Did you see it? The man escaping
So,
the country. Okay. See, that has nothing to do directly with our studies, but still, it may help us to draw some analogy. Okay, so this entire region is what? It is a depletion region. No man's land, you can think like that. No one is allowed to roam here. And these may be the, you know, people securing the border. Fine. So you can see here towards the right, that is, this is the inside. Okay. In the depletion region, in the inside, there is a accumulation of positive charge, isn't it? See, a layer of positive charges are here, and here there is accumulation of negative charges. And these charges are confined to this particular space, isn't it? So there, this is sometimes called as the space space charge. Charges accumulated in a particular region. Hmm. So just mind graph. I have taken my origin at the junction, hmm, and along this side, I'll be plotting the you can call the distance from the junction, and this way I'll be plotting the space charge density. I hope it's okay. And this is the origin. So, as far as the norms of a Cartesian coordinate system is concerned, uh, while plotting the graph, what we do, this side is negative for x, this side is negative for positive for x. So let me assume that this is the last point of the depletion region in the p side. That is, the depletion region at the p side is from this junction to this point. So let me call this distance as minus xp. I hope you all are okay with this. This distance I am calling minus xp. Why minus? Because it's on the left side. Suppose uh, this is the border 1 kilometer towards one country. So this is how much? 1 kilometer minus one because it's towards the left side. Is it clear, everyone?
Yes, sir.
Yes, sir.
Similarly, let it's just an assumption. Let I mean these names let the same thing be called xn. That is say 2 kilometer or 1.5 kilometer to the right towards the inside. We are not assuming that the distances are equal. So what is happening from here to here? We have positive charges accumulated in this region. Okay, put a plus here. So suppose I have this much positive charge. This accounts for this immovable charges. Similarly, on the p side, I have a accumulation of negative charges. Got it? Fine.
Yes, sir.
Okay. So that's about the charge densities. Next, we would be seeing the potential. So this is the junction thing. These kind of graphs are very useful when we plot when we draw a diagram and we plot the graph, keeping in mind the points, important points. I would have drawn this graph on the left side, but this is more meaningful. Anyways, similarly, if I want to plot the potential, write in details potential Vx, and similar this is x. Okay, same thing. This is the distance from junction. If I plot, same it is minus xp xn origin. Obviously, things on the upper side would be positive. That is potential above the origin is taken to be positive. Below it, it is taken to be negative. Okay. So what happens on the inside? What happens to the inside? Hmm. That's the diagram. Okay. So inside will not allow any electron to move towards it. Okay. Last day we got this thing when we are making for just forming the junction. What is happening? Holes from the p side, which are in majority, are going towards the inside, and electrons being more on the inside, they are going towards the p side. Then they're recombining, and when equilibrium is set, what is happening? This depletion region is formed, which does not allow any majority carrier to move from the relevant region. That is, holes can move from the p side to n side, and electrons can move from the inside to the p side. Remember this thing.
Yes, sir.
Yes, sir.
That is, for the holes, it is facing a very highly consistent positive potential. Positive and positive will repel each other. That's why the potential on this side is taken as positive, say plus Vn, this one. Similarly, this side is maintaining a consistently negative potential so that electrons can't enter. This side is taking a, I mean, having a negative potential. I'm calling it P, it's on the P side and on the N side. Hmm. Now, what about this region? So here, we just see it in details as well. Why the potential at the junction, I mean, how, why is the transition thing like this? Hmm. We'll see it very soon. So if you plot from, I mean, V, this means that this expense is how much? It is modulus of Vp. Yes, I'm writing the magnitude. And this is what? This is the magnitude of Vn. That is how we plot the graph. If I say this is, say, minus 10, what does it mean? If the y coordinate is minus 10, it means that from here to here it is minus 10. Similarly, from here to here it is Vn. Not minus 10, 10, the magnitude. Is it clear?
Yes, sir.
Now see, why is this thing like this? I mean, this region. You can understand it, why it should be like that. Now, going back to the video, which I said that we can draw an analogy with the same, with the case of minority carriers. That is on the inside. Yeah, the larger number can't move. What is in smaller number? The holes, isn't it? The inside has very small amount of holes, and the p side has very small amount of electrons as minority carrier. So what I said that it is possible that any one or two, maybe very few number of holes on the inside, they have acquired enough energy to reach the junction. Okay, why am I saying enough energy? Because see, the junction is accumulated with positive charges. Hole is also positively charged. So how can it can't on its own accord, reach the junction. It has to have some energy, like the person who somehow could manage to reach the border. Then what I said, once the hole somehow it reaches here, it will see there's a consistently huge amount of negative potential. It will be as easily attracted and it will move this way. See, that is, once the hole is here, the potential is such that it will easily attract it to the p side. Okay, you just, if you are a hole, you have to just reach here, then automatically you will fall to the p side. Got it? Did you get what I am talking about?
So can you explain it one more time, sir?
Just the hole has to reach the junction at, sorry, the depletion region. Okay, once it reaches here, what it will see, it will see there is a negative potential on the other side. Then it will be easily attracted that way and it can move to the p side here. Once it reaches the junction, it can see there is a possibility to reach the p side. Is it clear now? Because
Yes, sir.
holes will move from higher potential to lower potential. That is the nature of positively charged particles or quasi-particle as a whole. Similarly, for the electron, if somehow it reaches the near the junction, it will be attracted to the inside. But electrons move from lower potential to higher potential. So don't compare this diagram with a normal slope. That is, gravitation is pulling it down. With that analogy, you can never say that a hole can move from here to here on its own accord. Okay, it's not like that. That also violates the second law of thermodynamics. That water at the bottom of a waterfall can't on its own accord reach the top. It's not like that. Actually, for electrons, moving from lower to higher potential is the tendency. So that is all regarding the uh, potential. And if we can plot the electric field, how can we find the electric field from the potential? What is the formula?
QV.
minus del phi, sir.
Yes, electric
QV,
field from
sir.
potential. Sorry, Shravan, I didn't get you. Your voice is getting cracked. Anyone? How can we find E from V, electric field from potential?
Minus del phi, sir.
Right. So this thing is constant. This is also constant. Derivative of it would be zero. So no potential, no electric field on the left and right origin. Here it would be like this. It would be like this. Later on, we'll just see why the nature is like this. We'll be seeing it very soon. So that is all regarding these graphs are very important. Okay, so maybe you sit for an exam in the coming days for higher study. Then these kind of graphs may be given to you. You have to choose the correct one. I'm giving you a minute to draw the graph. Okay, after that I'll just resume the main topic. Just take a minute to draw the graphs. Done, everyone?
Yes, sir.
Okay. So now coming to the main topic, thing is that there is a potential which acts as a barrier at the junction to, just stop any further flow of majority carriers across the depletion region without any external assistance. The meaning is that without applying any external agency like electric field or light, we'll focus over electric field only for the time being. Without giving any external aid, it's not possible for the holes to go from P to N side and the electrons from N to P side. So you can see there has been a potential which acts as a barrier to the majority carriers. Hmm. So this is how much. There's the Vp and this is the Vn. Overall, we have a potential Vb which appears at the junction. That is called the barrier potential. Okay. This is what we would be calculating. So why is the barrier potential is appearing at the first place? Because of this space charge which is being accumulated. Due to the negative charges, here we have a region of lower potential. Here we have a region of higher potential. Okay. This VB we would be calculating now. Is it clear, everyone, what we are trying to do? Any doubt, anything, please ask. These are very basics.
Yes.
Is clear, others, or any doubt?
Can you repeat it?
Uh, See what we have. A potential which is acting as a barrier. Barrier, that is, it's acting as an obstruction to the flow of or the diffusion of majority carriers across the junction. So on this side it is still the minus Vp point, till here it is still the plus Vn. Overall, what is the height? It's also called the height of the barrier potential. What is the overall potential? This much. So this much of potential acts as a barrier to the flow of majority carriers. Is it clear now?
Yes, sir.
It's sometimes called height, because if you draw see from here, it is easy to think in terms of height of the potential. And see this sorry, this distance is very small. Okay, I think a micrometer orders this depletion region. I have just exaggerated things, so don't think that sir is talking about the junction, but he is considering from this region. This region is very close to the junction, and to see what is going around it, we just make this thing bit enlarged. Anyways, so now to derive it, what we would be doing, we would be considering the open circuit condition. Can anyone tell me what does open circuit mean? Anyone?
No flow of current, sir.
Yeah, no flow of current. Actually, I have not connected any external this thing to an external circuit. Okay, or even simpler, I haven't added a battery from outside. As simple as that. So in the open circuit condition for holes, since we haven't added an battery from outside, or we haven't connected this to a circuit, more importantly, we haven't connected it to a circuit. Forget about the battery. Even there is no circuit. Circuit is what? It is a closed path for flow of carriers. So in this case, what do we expect from for holes as well as for electrons? Let us begin with holes only. Net current is zero. There is no net flow of current, isn't it? Are you getting my
Yes,
point? Why
sir.
the net current is zero? It is an open circuit condition. Hmm. There is everything. There is potential. There is internal, electric field. But there is no net, or that is overall current is zero. That is, if overall current is zero, then current densities will also account for nothing. That is, what was this thing called? This was called the drift current density, isn't it? Remember this thing, drift current density for holes. Remember this one? Yes or no?
Is it EDP, sir, or EPC?
EP mu P E. Just a minute, I have to decrease the altitude. Is it clear now? Priyam, then you were absent in the last class, maybe, where we found that the you know drift current density for a dr I wrote is like n mu n for holes, and same for for electrons, and for holes it was like p mu p e. So this density or this flow is balanced by what? By the diffusion current density. The second term also I think you remember. This is for the diffusion case.
Yes, sir.
That is, what are the reasons for flow of current, if any? One is the drift, second is the what? Diffusion. When they are balancing each other, there is no net current. So let us take both the things on the same side. Keep on deducing with me, okay? Don't wait for the video to end. So let me call this equation 1. I would have made a PowerPoint, just dictated you, but I am doing it with you only so that you can derive with me. That is the best simulation of offline class possible, which I feel. Okay. Now let us recollect. Let us recall the Einstein's equation or relation. What did it say? I hope you remember this one. Yes or no?
Yes,
Yes,
sir.
sir.
Okay. So last day I said that this would be helpful. Hmm. What I can do is that let me try to calculate dp from here. Let us put this value in equation 1. Uh, One thing can be done. Shall I call it equation 1? Okay, no problem. So putting in 1, what we would be getting? We would be getting E, E,
So can't cancel small e, sir.
sorry,
Like so in equation one, sir.
hmm?
And we cancel like small e.
Which one small e?
I said that one, sir. We could have cancelled no, sir, before.
Oh,
Only
here, yeah, we could have, but see, cancellation is a mathematical process, but
yes, sir.
if you don't cancel, if you cancel it, the the dimension of the two things may not be very meaningful. The meaning is that this is your whole current density due to drift, this is whole current density due to diffusion, and they are equal. Okay, physically this is the equation. Yeah, now would be obviously we have to cancel. Hmm. My meaning is my intention is to convey that don't write like p mu e equals to dp dp dx. Don't write without e at the first place. That is more important. Yeah, would be cancelling now. Minus e dp, we will be substituting this value. What I can do, I can cancel this and take things on one side. That is e mu p e equals kt up dp dx. Now this is also good. You can cancel the two things. Now let us migrate similar terms. That is, let's keep the p here. We actually want to calculate the you know whole density. And if we go it this way, e by kt e dx. I hope you don't have any problem with this.
No, sir.
Fine. So the good news is that E and V are related by this equation. So E dx can be easily written as minus dv without any problem. I think the equation looks very much simplified. Is it fine?
Yes, sir.
Okay, now we have to just simply integrate this equation. I can call it 3. No, let's not call it anything. Now the main thing is that what about the limits of the integration? That is very important. E by kt is constant. Here is the catch. Now we have to remember that what is xp, this thing, it is representing the p side, I mean till the depletion region, and xn is representing the n side till the depletion region. That is, here is the what I have here. I have majority holes, here I have majority electrons, and here I have neither holes nor electrons. So we will be assuming that at xn, at xp, which is the or minus xp, which is on the p side, we'd be assuming that sorry, that whole density on the p side, let me call it p with a subscript p, the whole density on the p side. Is it clear what I'm trying to say here?
Yes, sir.
And on the inside, the same thing. Inside it be p, and very comprehensive terms used, p the greater P stands for whether it is hole or electron, and the subscript stands for whether it's on the P side or on the inside. So what is my limit? P. I'm going from, remember, I'm going from P side to N side, here to here. So P, 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 N. And what is the potential on the P side? It's minus Vp. On the N side, it is Vn. I hope you are clear with the potential values. So do the integration. Dn integration dx by x is ln. So it is ln p limits is minus e by kt v with the limit vn minus vp. This minus sign is very important. Okay, the potential thing. Many people forget to give it, and they end up the wrong result. So if I impose the limits, it would look like this: minus e by kt. It would be vn minus minus vp. So it is like this. As I said that Vn plus Vp is the barrier potential. See here, Vn plus Vp, that is the total barrier potential. So simply here I will write it minus E by Kt Vb, where Vb is the it's sometimes it's called the contact potential as well. Contact stands for that junction thing. Contact potential difference, or more importantly, it is called the potential barrier or barrier potential. Got it? Yes or no?
So,
Yes.
so can you explain me that the thought graphs are on electric field one, sir?
This one.
No, sir, no, sir. Below that.
Below that. Yeah, what do you want to know?
These are graphs, sir. Electric field graph.
Acha, acha. So you can see this is a constant value. It is minus b, isn't it? This value is constant. It's a straight line actually, parallel to the x-axis. So if you do, what is the relation between E and V? This one. If you want to find the electric field here, hmm, it would be what? It would be E equals to minus ddx of a constant thing. That's why it is 0. This side also the potential is constant till xn. If you want to do the derivative of that constant thing, here also you will get 0. Okay.
Yes, sir.
Hmm. Now you want to, are you confused with this thing?
Yes, sir.
Yeah, we'll just come to that. Or you can also try yourself also. Why is this like this? And why is it on the negative side? Why is it on the negative side? You have to understand the physical meaning of that. Okay, we'll come to that. First, let us try to calculate the height of the barrier potential. Let's get an idea about the potential. So here, if I want to make the anti-logarithm of this one. So Pn by Pp would be, see, here is a small problem. If I write E, which stands for exponent, e to the power something, don't get confused that E with this E. This small is for electron charge, that would be for the exponent. So I'll just make that E like this, cursive. I hope you understood what does this E mean. This E stands for the exponential. E to the power x, e to the power minus x, that E. In many books you will see they have taken the electronic charge as epsilon for this reason. So what is the hole density on the inside? That looks like this. Fine.
Yes, sir.
You can easily see that there is no way on earth that Pn can be more than Pp. Due to this exponential sign, it will always be less than Pp. At best, it can be equal to Pp when this term is 1. That is also not practically possible in semiconductors. Now, you have to understand something. What did we say that the room temperature or the moderate temperature, some books call it moderate temperature, that gives sufficient amount of energy for many things, like the electron can even go from the, some electrons can even be detached from the bonds with that energy, some can even reach the conduction band. Another, hence what happens that at room temperature the energy is so high, the thermal energy, that we assume that there won't be any harm if we say that practically all dopant atoms are ionized. Meaning is that if there were two phosphorus atoms, obviously they are not neighboring atoms. I'm just giving example. If there were two phosphorus atoms in the overall specimen at room temperature, they all will become like this. And that is I'm talking about the inside. And had there been any trivalent impurity like boron, even at this room temperature only, all of them would have become completely ionized. Are you getting it? What I'm trying to say?
Yes, sir.
Actually, the ionization energy required, that is very low compared to the energy available. So see, now think the other way. Who is giving out the minority carriers? The dopants only, isn't it? So on the PP side, sorry, on the P side, what we can think? We can think that, sorry, who is giving out the holes? The extra holes, the dopants. So we can say that this is equals to this, where Na is the uh, acceptor atom per unit volume, the density of the acceptor atoms. Can you tell me why is it happening? Can you tell me why is it happening? Do you agree with me that accepted atoms will give the holes? Are you okay with this one? Hello, am I audible?
Yes, yes.
Yes, like
Yes, like?
if they come close to the junction, sir.
No, no, no. This is, I'm talking about this region, in the bulk of the P side, not in the junction. What happens to a P-type semiconductor? Okay, we'll be discussing in the next class. Okay, next class is already, I think, ready to go. Fine. Bikramjit sir is waiting. We'll discuss this in the next class.
Okay, sir.
Yeah, we'll discuss it
Yes,
in
sir.
next class. Fine. Okay, fine. It is from 12:10 the next class. Okay, we'll
Okay, sir.
discuss it.
Thank you,
Yes,
sir.
sir.
Okay,
Thank you,
thank
sir.
you.